Hello everybody, welcome to my 12th video. This is on Ternary SR, D-type, T-type and JK flip flops. Now first I'm going to demonstrate some test equipment that I've made. And first of all, you can tell this is a 5 MHz TTL oscillator which provides a clock signal for the flip flops, and also I've got a monostable which provides a negative going edge to clock the flip flop. That's for a single clock. Also I've got some switches which switch between logic 0, logic 1 and logic 2, and similarly here logic 0, ternary logic 1 and ternary logic 2. So first I'm going to demonstrate the SR flip flop. Basically, to set a logic 0, or sort of to set a logic 2, sorry, S is at 2 and R is at 0. This is at 0. This is S at 2, logic 2, and R at 0. So I'll just connect it. So that gives logic 2. And to hold the logic 2, I can select S to 1 and it holds the logic 2, and S to 0 and it holds the logic 2. To set a logic 1, S is at 1 and R is at 1, so that's S. This is Q, that's a logic 1, and I can either set S to 0 then R to 0 and it holds the logic 1, or alternatively I can set R to logic 0 and S to logic 0 and it holds Q, logic 1. To set a logic 0, R is at 2 and S is at 0. I'll just scope R is at 2, S is at 0, Q, that's the output, Q at 0, and I'm going to set S to a logic 1 and R and Q stays at 0, and S to logic 0 and Q stays at 0. So that's the operation of the SR flip flop. Right. Next we have the D-type flip flop, which I'm just going to wire up. Right. Right, so I'm going to wire it up and apply the power. Right, so I'm going to wire it to the monostable, and at the minute D input is a 0, so it holds a logic 0, that's the Q output there. This is the clock pulse providing a negative edge pulse. I switch the D input to a 1, the clock pulse, and turns to a ternary logic 1. I'm going to switch the D input to 2, apply the clock pulse, and the Q output turns to a ternary logic 2. So that's the operation of the D flip flop. The output Q follows the input D. Right. Next we have the T-type flip-flop. Right, clock. Right. Apart. Right. First of all, this is the clock to the flip-flop, the TTL 5 MHz crystal TTL oscillator, providing the clock signal to the clock, and I'm wiring one of the switches to the T input. So for ternary logic, with the T input at a ternary logic 1, the T-type flip-flop counts up from 0 to 1 to 2, 0, 1 to 2, on the negative edge of the going edge of the clock pulse. If I turn it to a 2, then it counts down from a ternary logic 2 to 1 to 0, 2, 1, 0, on the negative edge of the clock pulse. And if I switch it to 0, it happens to hold whatever the present state of the flip-flop is, of the output Q from the flip-flop. So if I turn this to the monostable, if I click it to a 1, the output Q will go to a 2, and if I make the T input a 0, then it holds a logic 2. If I hold a logic, set it to a 1, the 2 goes to logic 0. If I set the T input to 0, it will hold a logic 0. And if I set the T input to a 1 and clock it, it goes to a 1. And if I set it to a logic 0, it will hold a logic 1 Q output. So that's the operation of the T-type. It follows the operation Q plus. The next operation of the Q is after the flip-flop has been clocked, follows the operation Q plus T. Okay, so that's the T-type flip-flop. Lastly, we have the JK flip-flop. Right, I'll line this up. Right, I'll apply the clock. Right, apply the power. Okay, so we're applying the TTL oscillator to the clock. At the minute, J and K are at 0, 0 from the switches, so that holds the state of the clock, state of Q before the clock was applied was 0, so any consequent states are 0, it holds whatever state it is. So there are a few waveforms I can show you for this. Firstly, for set 2, the output should clock. There we go. that's a set 0, that's a set 2, sorry. Yeah, with j equal to 2 and k equal to 0, you see that's a set of 2, that's a ternary logic 2. And with j equal 1 and k equal 1, that's a ternary logic 1. And with j equal to 0 and k equal to 2, that's a ternary logic 0. Well, what are the outputs? So with j to 1 and k to 2, that's the counting up, that's q plus 1. The function performs q plus 1. So that's 0, 1, 2, 0, 1, 2, 0, 1, 2 on the negative going edge of the flip-flop of the clock pulse. So that counts up, and if I set j equal to 2 and k equal to 1, that counts down from logic 2 to logic 1 to logic 0 on the negative going edge of the clock pulse. And a few other things I can show you. With j equals 1 and k equals 0, if the present state of q equals a 1 or a 0, then the JK flip-flop will oscillate between logic 0 to a logic 1. Yeah, and with, take that to logic 2, with k equals 1 and j equals 0, if the output Q starts off with a 1 or a 2, then it oscillates between logic 1 and logic 2. And if I can do it with, I'll go with j equals 2 and k equals 2. If the output Q starts off at a logic 2 or logic 0, then it oscillates between a logic 0 and a logic 2. Right, I'll just show you how it holds. So I'm going to change the clock to the monostable. So I'm going to reset the output Q to 0 and set J and K to 0. It holds a logic 0. I'm going to set J to 1 and K to 1, and the output goes to logic 1. Now I'm going to set J to 0 and K to 0, which is the hold state, and it holds a logic 1. Now I'm going to set J equal to 2 and K equal to 0, and that goes to logic 2. I'm going to set J equal to 0 and K equal to 0, which is the hold state, and the flip-flop's clocked and it's hold a logic 2. Right, I think that concludes the presentation. I don't think there's any other things I can go through. Well, that's it. Well, thanks for watching. I hope you enjoyed it. Bye.